Should be good to go. Give me just a moment so we can kick off, get everything going on YouTube. We are live on TikTok. Let me send it an announcement. Let's go here and then do this. Hello, hello. Just getting everything started. We should be good to go soon. And we'll give it some time so people can stream in. Grimlock, thank you for the $5. I appreciate you. As always, like single-handedly funding, let's get a W for Grimlock. Single-handedly funding this live stream. Well, this Grimlock and Fierce Interaction and Robert Knatzer and a few other regulars are keeping this going. How's my audio? Hope it's okay. Yeah, remember to like the live so then we can get more people in here so we can start sooner. We usually start when we get to around 100 viewers on TikTok, 100 concurrent viewers on TikTok anyway. Audio is 5x5. I don't actually know what that means. I realize. Like that doesn't mean anything to me. All things considered. There's probably some meaning that I'm missing, but anyway, today we're going to be talking about joint classical quantum systems. I'm not so new about that. I'm not so knowledgeable about this, so we'll have some learning to do together. Are we exiting the black hole that is supposed to be the new discovery that we are in one? Go watch my latest video. Finally finished my QFT playlist. Hey, that's cool. I'm glad. It's from the CB Radio Days meeting. It's good. Ah, 5x5. Okay. Have you published any papers? Yeah, like a lot. In fact, I just had one come out yesterday, or at least it was uploaded to the preprint archive. I literally posted it an hour ago. So the answer is, it's not even clear that we're in a black hole universe. Please respond to Dr. Sweater. I don't think that did he stitch me or something, or did he call me out? I don't think that he did. He's not like a big creator or anything, so it's like, are you familiar with Stephen Wolfram's work? Yeah, it's, well, like mildly. Nobody really worries about it though. Black holes fascinate me. Me too, but that doesn't mean that we're in one. Are we supposed to be able to see that? No, no, no. I'll zoom in once we get going. This is just, a starting page. Are you a guy or a girl? Well, I have a deep voice and masculine facial features, so if you were to guess, you'd probably guess correctly. Hey, do you agree Jesus was a real person? Yeah, probably. Okay, we should probably start. Yeah, let us get started in just a moment. Okay, so today we're going to be reading a paper by Masahiro Hotta, Sebastian Murk, and Daniel R. Terno. The paper is called Classical Quantum Systems Breaking Conservation Laws. So we're going to be talking about things that are joint between classical descriptions and quantum descriptions. Hey, from Robert with the $2 super chat. Thanks for the great content. Thanks, Robert. I appreciate you. So let's just read the abstract and then we can talk about it and then we'll get into the details. I haven't pre-read. I never pre-read. I just make sure that there's not too much mathematics because that makes for a hard reading experience for everybody watching. So let me just, so it's going to be hard to see for now. Once we get into because it's a 2-column format, it'll be easier to see what I'm reading later. So just bear with me for now. Let me just make this 150. There we go. Right. So whether gravity must be quantized remains one of the biggest open problems in physics. Yeah, we're talking about quantum gravity. Classical quantum hybrid theories have recently attracted attention as a possible framework in which gravity is treated classically, yet interacts consistently with quantum matter. Yes, reviews are on Tuesdays. It's just last week was a little bit different. Schemes based on completely positive dynamics satisfy most formal consistency requirements and enable a systematic treatment of quantum back reaction, but they also give rise to features that challenge conventional physics intuition, such as the breakdown of conservation laws. To illustrate this issue, we consider a qubit interacting with a classical particle and demonstrate that the corresponding hybrid system violates angular momentum conservation despite the rotational symmetry of the underlying equations of motion. So what's going to be gone over here is essentially they're going to use a toy model, which is one quantum particle and one classical particle, to demonstrate that even though you might expect there to be some sort of conservation laws, like angular momentum conservation, it fails to have that conservation law because of this weird interaction between classical and quantum systems. I don't know how they're going to do it. I'm not even that familiar with positive dynamics, so hopefully they'll explain it. But let's read and see what they have to do. And yes, this is on YouTube. It's multi-streaming both there and here. Right. Okay, so we can zoom in and so we can read a little bit better. Hopefully this is more legible, I guess. So, if you don't already know, oh, I should remind everybody, if you want to read this paper, if you want to follow along yourself, type this number, this code into Google, ARXIV colon 2506.15291. Punch that into Google, you'll find it'll be the first link that pops up. And you should be able to find this. So let's read. And don't worry, I'll go slow. I'll explain things as we go. Ask questions if you have them. We'll do what we can. Right. So, a consistent mathematical description of the mutual interaction between classical and quantum systems. So that's kind of self-explanatory. So we have a description, a mathematical description, that's how we do physics, of an interaction between a classical and a quantum thing, known as hybrid dynamics, is thought of either as a computational tool, as part of a resolution of the quantum measurement problem, or as a fundamental theory if the gravitational field remains at least partially classical. Yeah, so I guess the point is that this kind of classical quantum interaction business, this can be used for a bunch of different purposes. Hybrid models must satisfy certain axioms, but their degree of compliance depends on the intended purpose of the model. One sec, let me shut my door so then I don't wake up my wife. I just don't want to disturb her. She didn't sleep last night. Right. In computational applications, a hybrid scheme only needs to remain valid for the duration of the investigated process, although full consistency is still desirable. So that's referring to this first example, a computational tool. In contrast, a hybrid model aiming to describe a fundamental theory of gravity must meet stricter requirements, while models developed for other purposes may not be applicable to the processes that involve gravitation. So this is just to say, there's pretty stringent requirements if you're actually going to use this to talk about, say, quantum gravity, which is what they're going to kind of try to model, not explicitly gravity, but talk about something that could potentially be used for quantum gravity down the line. They're going to use the same requirements on their toy model. Right, so approaches to classical quantum, they're going to abbreviate it CQ, dynamics, broadly fall into two categories. Reversible, unitary, and irreversible, completely positive. So, well, let's read the paragraph and then I'll explain. The former seek to establish a mathematically consistent counterpart to both fully quantum unitary and fully classical Hamiltonian theories while avoiding dissipation and diffusion. However, all known reversible schemes are generally inconsistent. Okay, well, that's not great. Even when partially valid, they require the classical system to possess some minimal uncertainty. Yeah, okay. Moreover, there is strong evidence that coupling a classical system to a generalized probability theory, and not just quantum mechanics, necessarily introduces irreversibility. So the point is that typically we think of quantum mechanics, at least in the traditional sense, we think of it as being reversible. So any quantum operation that you can happen, except measurements, but measurements we generally don't consider when we're talking about like conservation laws and things like that. So, well, I mean, we do, but for separate reasons. Generally, quantum behaviors, quantum dynamics are reversible. You can run them forwards and backwards, and it's the same dynamics. On the other hand, we think of like actual thermodynamics, classical things, as being irreversible. So the point is that if you wanted to make a completely reversible theory of classical quantum dynamics, apparently that leads to some problems. They're generally inconsistent. On the other hand, if you allow for irreversibility, if you allow for systems where you can do something but can't undo it, well then I guess there's not necessarily an issue. So presumably that's what they're going to do. They're going to use completely positive dynamics. Hopefully they will explain that fairly well. Right. So recently, Oppenheim, you may remember this name. There was Oppenheim, Oppenheimer, and Oppenheimist. Oppenheim was the one who talked about a classical theory of quantum gravity, which was interesting. I never made a video about it, but it was all the rage like last year. So recently, Oppenheim and collaborators proposed a completely positive hybrid scheme that satisfies most consistency axioms. Those axioms are going to be summarized in Appendix A2. Maybe we should go look at that. We'll look at it after this paragraph, or maybe after the introduction or something. This approach has been Thank you for the community fest. This approach has been successfully applied to scenarios requiring the back reaction of quantum fields on a classical background, and has also provided potentially observable bounds on gravitationally induced decoherence. So, by the way, C-bar, we can see your message. So the point is that the reason why they're investigating that here is because this is something that was done recently by Oppenheim and collaborators to try to talk about like a non-quantum quantum theory of gravity, or rather a non-quantum unification of gravity and quantum mechanics. And so they kind of want to test it and probe that idea. Does it actually work? Now let's think about this for a bit. Yeah, so we should probably go look at the appendix. What was CP again? CP was completely positive. That's right. Okay. So let's go look at the axioms just to make sense of this. So they'll refer to Appendix 1 later, I think, but we should look at Appendix A2 just that way then we can actually get some, yeah, so we can figure out what these axioms are. Right, so the most commonly imposed consistency conditions on hybrid dynamics, these I guess are discussed in these two, ew, gross. In these two references, these include both formal mathematical requirements necessary to ensure well-defined entities, so you need some mathematical rules, and then also physical ones motivated by embedding the hybrid model into a broader theoretical framework. I guess these include things like compatibility with the laws of physics and in particular conservation laws. The most basic purpose of any CQ hybrid scheme is to obtain predictions about the evolution of the classical and the quantum subsystems, and the results of measurements performed on them. To this end, any hybrid scheme must identify the classical and quantum sectors, as well as to produce 1. A phase space probability density, we'll call this curly rho, that satisfies curly rho is greater than 0. So this is a probability thing. And if you add up the probability of all possible locations, then you get 100%. That's what this integral means. And 2, a positive semi-definite operator straight rho. Oh, we need a new letter for this. A new name for this, because curly rho and straight rho will be really annoying. Okay, well, we can just say that. A positive semi-definite density operator. So that's a big, long language for a matrix. And the matrix has certain properties, namely it has eigenvalues that are positive. So it has eigenvalues that are positive or 0. That's what it means. And it should satisfy that the expectation value of some operator acting on the quantum system described by the density operator. So you describe a quantum system with a density operator. You describe the action of an operator, that operator meaning that operator kind of corresponding to a measurement of some kind. So the average value of the measurement, that's what the expectation value of that measurement with respect to the density operator rho is. This should be the trace of the product of the two matrices. So the operator A is a matrix. Rho is also a matrix. So rho describes the quantum system. A describes the measurement. So if you take the product of the two, and then you take the trace over the resulting matrix, that should give you the average result of the measurement. And that should be true for every operator A in the Hilbert space, H. So these apparently are derivable from the state rho hat of the combined CQ system, and they represent the information about the states curly rho, which is the classical state, and straight rho, which is the quantum state. or the quantum, so there's the classical subsystem and the quantum subsystem, indicated by curly row and straight row. Each individual sector behaves in the usual way. So for a closed CQ system, if C and Q are uncoupled, meaning that you have a classical stuff and you have quantum stuff and they're not talking to each other, then the classical stuff obeys classical laws and quantum stuff obeys quantum laws. That's one axiom. Another axiom is that the classical canonical transformations and quantum unitary transformations are realized on the classical and quantum sectors respectively. This just means that you can do like the normal things that you would do to each separate sector. There's a few more axioms. We need that the evolution of the classical quantum system may or may not be unitary. That was described in the introduction. Essentially, we're going to require that it's completely positive rather than unitary. Unitary is sort of equivalent to reversible. So it may or may not be unitary, and only one of the Schrödinger or Heisenberg pictures may be accessible. So when we talk about Schrödinger or Heisenberg pictures, these are different ways of thinking about the evolution of a quantum system. So on the one hand, you can talk about the quantum system being unchanged in time and the way that you perform measurements changing in time. So your measurement outcomes change over time. That would be the Heisenberg picture. On the other hand, you can talk about the measurements not changing in time and the quantum system changing in time. That would be the Schrödinger picture. And so it's saying maybe only one of these will be usable. But despite those two features, the fact that it might not be unitary, the fact that you might only have access to one of these two kind of pictures of quantum mechanics, it should still conform to the laws of physics. In particular, it should satisfy standard conservation laws, it should maintain the impossibility of superluminal communication, and it should obey the second law of thermodynamics. So these are all really kind of good expectations for any law or any theory of physics. You would want these things to be obeyed. Furthermore, we have that a hybrid dynamics may introduce back reaction of the quantum system onto the classical system only if the CQ correlations are generated dynamically. So essentially, if the relationship between the classical system and the quantum system change over time, that's the only way that you should be able to get an effect of the quantum system and the classical system or vice versa. And that can be reframed in terms of the statement that the quantum purity, which is a statement about essentially whether the quantum state is in a mixture of multiple quantum states, a statistical mixture rather than a superposition, or whether it's just a pure superposition of quantum states. So you can evaluate that by examining the quantum purity quantity, which is the trace of the density matrix squared. This shouldn't, if this changes over time, if the purity changes over time, meaning it goes from pure to impure, then you could have a back reaction from the quantum system onto the classical system. And I think that there's going to be a few more axioms. I guess one more axiom. The axioms are going to be complicated, but we'll get to the details and it should be fairly simple once we actually get through it. But we do have to go through the axioms just so we know what to expect. So the last thing that we need is, although unitary evolution preserves the purity of the combined CQ state, so again, purity means something like that your state is describable as a superposition rather than as a statistical combination, it may act non-trivially across the C and the Q subsystems, thereby generating entanglement. So you can have entanglement between classical stuff and quantum stuff. I guess that's what they're saying. Requirement 6, this is an axiom, thus represents the minimal necessary conditions that allows for non-trivial interactions between the C and the Q subsystems. That's what this axiom is saying. That you need to have some sort of mixing between the classical system and the quantum system, and that's captured by the fact that the quantum system evolves from a pure quantum state to a non-pure quantum state, to a mixed quantum state. While the minimal goal is to produce reasonable probability distributions, having access to the Heisenberg picture, i.e. explicit evolution equations for all observable operators, is a desirable feature. So probability distributions you get from the Schrödinger picture. The Heisenberg picture tells you how your observables, the things that you measure, change over time. So you kind of want both. So in this case, they demand the following, that differences in the predictions of the quantum and hybrid equations of motion for classically unobservable quantities vanish in the formal limit h bar goes to 0. Meaning that, so if you did a purely quantum observation or a purely quantum prediction, as opposed to a hybrid prediction, for things that are generally not observable classically but are observable in a quantum way, like entanglement, those things should be 0 when you set the Planck constant to 0. Basically, when you turn off all quantum behavior. Thank you for sending a sub, Momo. I appreciate you. Failure to comply with this form of the correspondence principle leads to a breakdown of the classical limit. So this is just the idea that you can, if you let quantum effects go to 0, then you should reproduce classical physics. Right, so those are the axioms. There were a lot of them, but we can now actually get to the meat of the matter and see what they have to do. Now, I have a feeling that they're actually going to have axiom 5, which was the conservation law one, be violated. So that's what it said in the abstract anyway. So let's read. So the CP evolution, remember CP stands for classical, or sorry, completely positive. I should just say completely positive. So the completely positive evolution of the combined system ensures compliance with the technical axioms 1 through 4, 6, and 7. However, a completely positive description comes at a cost. It prevents full compliance with conservation laws, which are at the heart of axiom 5. Indeed, it reduces the dimensionality of the manifold of steady states, violates certain conservation laws, and predicts dissipation of gravitational waves propagating in a vacuum. Those are some pretty big, pretty significant bad things. Bad in a certain way. I just spilled water all over myself. Was my water bottle seal not tight? Oops. How did that happen? Okay. Yeah, I don't know why my water bottle's spilling or leaking. Okay, I think we're good. By the way, if you're just joining us, we're reading the introduction of this paper. The paper is called Classical Quantum Systems Breaking Conservation Laws. And if you want to follow along, just pull up this, type this text into Google. It'll be the first thing. Also, you can go watch on YouTube. If you go watch on YouTube, you can rewind and go watch, from the beginning. Just so you guys know, I'm not like an official reviewer of this paper. This is like public outreach that I do, where I kind of review preprints. These are not yet published. They haven't even been peer reviewed yet, but we can still read them and think about it. Oh, you're just having a coffee table chat about this paper. That's fun. Yeah, so we'll see what I have to think about it. So, right. Right, so if you have a classic or a completely positive description, then there are some costs. Your manifold of steady states is smaller than expected. You violate some conservation laws, and gravitational waves are dissipative. Weird, but okay. The mathematical formulation of completely positive dynamics is in infinite dimensional spaces is highly non-trivial, and incorporating Hamiltonian dynamics of the gravitational field adds further technical challenges. Yeah, probably. In this work, we therefore focus on conceptual issues using a toy model and leave the full dynamics of the coupled matter-gravity system for future research. So CP stands for completely positive. Get your brains out of the gutter. Things are allowed to have abbreviations, right? No, we're not talking about breaking conventional laws or breaking. So conservation laws are not like generally are not like sacrosanct, right? Like there are things that we are able to do that don't have conservation laws, right? The remainder of this article is structured as follows. In section 2, we briefly summarize the mathematical formalism to describe the dynamical evolution of quantum or of classical quantum hybrid systems, and we introduce the notation. That's pretty normal. In section 3, we discuss steady states and conservation laws in the framework of completely positive dynamics, along with comments on fundamental issues. In section 4, we provide an example of a toy model that violates conservation of angular momentum despite rotational invariance of the underlying equations of motion. And lastly, in section 5, we summarize the physical implications. Momo, thank you for the gifted sub again. Lastly, in section 5, we summarize the physical implications of our results and outline possible avenues for future work in this domain of research. Okay, great. This is how you write a paper, by the way. If you were interested in, getting into physics and you want, or physics or even math, well, yeah, this is how you write a physics paper. If you're interested in writing physics, at least a short physics paper, your introduction is going to go over some historical stuff, why it's relevant, going to have a lot of citations, and then your last paragraph is going to summarize what you do in which section. Them's the rules. That's how you do it. Right. So let's read section 2. So we're going to talk about the dynamics of classical quantum systems. So there's going to be some math here, but I'll walk you through it. Don't worry, it won't be so hard. So before we consider the dynamics of a combined CQ system, we set the notation and detail the description of its two subsystems. The classical system on its own is described by a phase space B. That's a horrible letter. That's called fractor. That's the font there. It's the letter that's used sometimes for phase spaces. It's a B, which is a 2 n-dimensional Poisson manifold. So we'll have to go over this, but it's think of its particular type of geometric space, and it has 2 n dimensions. N is going to be the number of dimensions that the thing lives in. So if you live in a three-dimensional universe, then you will have 6 dimensions of your Poisson manifold. And the reason why is because the Poisson manifold has coordinates. So we talk about a place on the manifold. A manifold is like a higher dimensional version of like a geometric shape. It can be curvy, it can have different geometric features. Don't worry too much about that. The point is that you can describe a point on this Poisson manifold in terms of both the position of the particle and its momentum. So both the position and the momentum, so position x, y, and z, and then momentum, which is a vector, so it has 3 components. Momentum in the x direction, momentum in the y direction, momentum in the z direction. Those together form a single point on your Poisson manifold. That's what a Poisson manifold is. It's basically a way of describing both the position and the momentum of a classical trajectory in a nice geometric way. You can also do this. I think that they're actually... this seems like the exact same thing as a symplectic manifold. Let me just double check, because it seems like we're just doing symplectic, but I know that there is a difference. No, a Poisson manifold is a symplectic manifold equipped with a Poisson... no, I'm sorry. They are similar. They're not quite the same, though, because a Poisson manifold has a Poisson structure, which is a type of bracket. It's a way of evaluating the action of operators on densities, basically. It's sort of like the classical equivalent of... Yeah, the Poisson bracket is the classical equivalent of the commutator of 2 quantum operators. So this is sort of like the classical thing that you would like to do. It is basically a phase space. A phase space is described by a Poisson manifold. That's like the language that's used. I guess these were introduced like 50 years ago. I thought that it was more recent than that, or older than that. Yeah, so Poisson manifolds are a broader version of symplectic manifolds. Symplectic manifolds are basically what you would call a phase space. Poisson manifolds have extra stuff. Right. So, but I don't think that we'll actually need to get into the details of this. We won't need the details of like how Poisson manifolds behave, I don't think. But we'll see what he does. Right, so we use the measure dz without specifying its explicit coordinate form. So basically, if you guys remember from calculus, if you've taken calculus, you have a measure whenever you're doing an integral, which basically tells you how big a square is in your space. So if you're doing like a 2D integral, like an integral over an area, you might have a dx dy. Now the dx dy is the measure, and it basically gives you like the number, the 1 in front of the dx dy. That tells you how big a little square of side length dx and side length dy is. That's the rough idea, and so the measure dz is basically tells you how big a little chunk of this Poisson manifold is, how much space it takes up. And they're just going to call it dz without giving specific coordinate form. Fine, that's pretty normal. Momo with another gifted sub. Thanks, being so generous. So the states of the classical system are given by the I can never say this. The Louisville. I'm going to say Louisville. The states of the classical system are given by the Louisville probability density curly row of z. So you'll plug in some position and some momentum, and that will give you a probability, or that will give you a way that you can measure the probability of your state being at that position and having that momentum, right? That's the rough idea. For a closed system, closed meaning that it's Leoville. I don't know if that's right. Anyway, I'm gonna say Louisville, because it's French. For a closed system, meaning that energy is not coming in and out, that nothing's affecting it, the usual stuff. The evolution is generated by some Hamiltonian, call it H subscript CL for classical. A precisely known classical trajectory is represented by the distribution rho of z and t is delta of z minus z naught of t. Now, there's a few things here. So if you have a precisely known classical trajectory, not some like statistical amalgamation of a bunch of different classical trajectories, meaning that you have complete knowledge about the path the classical thing will follow, that means that both its position and its momentum are entirely specified along the entire trajectory. Now, in order to describe that in terms of a probability density, what that means is that you need to say the probability of being exactly this way is 100%, and the probability of being any other way is 0%, right? Now, we need to capture that, and the way to capture that is with a Dirac delta function. Now, I don't know if you guys know what a Dirac delta function is. I can show you. We can just pull up a picture. A Dirac delta function is something like the limit of this guy. So imagine that you have like a bump, but the bump gets narrower and narrower, and you take the limit as the bump gets infinitely narrow, right? And so basically just have a sharp peak in one place, and it's 0 everywhere else. And so all they're saying is that that peak should occur when the argument of your Dirac delta is 0. And so if we know the classical trajectory, call that z naught. So that tells you the position and momentum of your classical particle at all moments of time. Then that means that the probability density should just be whatever coordinate minus that. So if the coordinate z, which tells you about the position of momentum, is exactly what you want it to be, then you're at the spike, you're at the peak of the spike. And if it's not exactly what you want it to be, then the probability is 0. So it turns out that if you integrate this thing, you get exactly 1. So the probability of landing exactly at that spike is 100%. The probability of landing anywhere away from that spike is 0. That's what it means to have a precisely known classical trajectory. But you can imagine that your classical trajectory is only known to a certain extent, maybe because your instruments have a certain amount of error in them, and so there will be some statistical description of your classical trajectory that says, well, there's a 95% chance that it falls within this particular trajectory. Man, this guy, the man, the legend, none of you are here to listen to this. You're just pro-LGBTQ and supporting this guy. I'm not a member of the LGBTQ, but that's cool. And also, like, completely unrelated to the topic, so I don't know. You don't have to be here, but thanks for giving me the view, I guess. Right. So that's the classical description. Now we can do the quantum description. A quantum system is described on a separable Hilbert space H. So you use curly letters for spaces. So you use a curly B for the Poisson manifold that describes the classical mechanics. And you use a curly H, or a fancy H, a pretty H, for a Hilbert space. Information about its state is contained in a positive trace class, trace 1 density operator rho. So we describe the dense 1 operator rho. Sorry, let me back up and explain. So in the same way that you describe a probability function that takes as inputs the position of momentum in the classical way, we need some way of describing potentially statistical descriptions of quantum systems, because you can have a quantum system that you have some uncertainty about, not like quantum uncertainty, like normal uncertainty. You just like, maybe when you prepare the quantum system, your instruments have a little bit of error, and so there's just a little bit of uncertainty in the preparation. So that would be what's called a mixed quantum state. So we want to be able to describe not just pure quantum states, which are sort of like laboratory ideals, but also mixed quantum states, which include some details about, like the instrument error in producing that. So the way that you describe that is not with a state vector in a Hilbert space, like you normally would, but you describe it as a matrix operating on, I know it's laggy, sorry. You describe it as a matrix operating on vectors in the Hilbert space. And that matrix is the density operator rho. Now, that density operator rho has to have some properties, sorry. And those properties include things like it has to have positive eigenvalues. Basically, it means it has to be a positive probabilistic combination of quantum states. It has to be trace class, which means that its trace has to have certain properties. And when you take, it's the square of its trace has to have certain properties. And then when you take the trace of the density operator, meaning that if you add up the probabilities of being in each quantum state, you get 100%. So that's what trace 1 means. So those are the two different descriptions of the classical and the quantum pieces that are going to go into this description. And then I guess they're going to follow references 6 and 7, right? So following references 6 and 7, we describe the state of the classical quantum system using a density operator rho hat. So this will presumably describe the whole thing. That in the Schrodinger picture, remember the Schrodinger picture tells you how the state evolves in time and the operators are unchanging. So in the Schrodinger picture, this density operator rho hat depends not only on time, but also on the classical variables z in the Poisson manifold. So typically, we describe a density operator on a purely quantum system. It just depends on time. It doesn't depend on any like coordinates or anything. But because this thing is also supposed to capture some classical bits, we're going to have it depend on the coordinates as well. Right. So the states of the classical and quantum system are obtained via this. So we have the full classical quantum system, and then we want to be able to describe the classical and quantum subsystems. So remember the classical subsystem. Oh, are we lagging? Are we good? So the classical subsystem is curly rho, and the quantum subsystem is straight rho. So in order to get the classical and quantum subsystem descriptions from the whole description, on the one hand, we could just take the trace of the density operator rho hat, and that will give us just the classical system. And the reason why it does that is because the trace of the quantum system, the part that makes it a matrix, is 1. So essentially, the matrix part of this thing, so this is now a matrix that depends on z and t. So if you take the trace of it, you're just basically multiplying the classical thing by 1, and you're getting rid of all of the quantum degrees of freedom. And so that's how you get the classical description of the classical subsystem. On the other hand, if you want to view just the quantum piece, then all you have to do is you just add up all of the contributions over the entirety of the classical system, because those are just a whole bunch of probability stuff. And so you want to integrate over all of the possible positions of momentum to get rid of the position of momentum dependence of your operator. So here you're going to integrate over z, which is all of the positions and all of the momenta. And that will get rid of that dependence and give you just the classical or just the quantum subsystem. Right. The classical quantum state is normalized. So apparently, if you do both of these together, so you integrate and take the trace, you should get a 100% probability. That's what it means to integrate and take the trace. You get 1, probability of 1. Is it glitchy? It doesn't look like I'm dropping any frames. Yeah, so this has obvious extensions to the expectation values of various operators. When it says obvious extensions, what that's going to mean is it's going to mean, where is it? Okay, well, I'll just explain. So when it says obvious extensions, you would just multiply your, or you just act with your quantum or classical operator in the form of a matrix by multiplying that matrix that denotes the operator or the measurement by the density operator rho hat, and then you take the trace. What's the Poisson manifold? The Poisson manifold describes the classical degrees of freedom of the classical quantum system. It describes positions and momentums. Right. Further mathematical details related to the structure of hybrid systems are provided in Appendix A1. Let's go look at Appendix A1 and see if I can hand wave it away, so that we don't have to read the whole thing. So let's just see how much is there to do. Okay, there's not a lot in Appendix A1, so maybe we just read it and I'll explain what's going on. So this is just talking about the mathematics. So classical states and observables are phase space functions. So yeah, the idea is that you have a classical state is a function of positions and momentums. And that function, the classical state will tell you the probability of being at that position and at that momentum at some particular moment in time. More precisely, oh yeah, it says it here. More precisely, classical probability distributions curly rho of z and t on the phase space B, remember B tells you positions and momentums, are either integrable functions or they are tempered distributions such as the delta function, normalized such that the probability of finding the state in some possible state is 1. A tempered distribution is just something that is technically infinite, but you can still integrate it. This Dirac delta function, remember, it's just an impulse. It's a very, very sharp peak, very, very sharp spike, and it's actually infinitely sharp at the point where it's peaked, and it's 0 everywhere else, but you can still integrate that. And so this is all to say that you can integrate the probability distribution, and that will get you to 100% probability once you integrate over all possible positions and momentums. Beyond observables such as Q and P, so Q is position and P is momentum, and their respective functions, so you could, for example, measure the position, the average position of your classical system by applying the Q operator, which you would just multiply Q by the thing that you're trying to, or by your probability distribution, and then integrate. That would give you your average measured value. We need linear, multiplicative, differential, integral operators on phase space functions subject to appropriate restrictions. Their space is denoted by curly f, the space of operators, on B. So you can have normal observables, which are just combinations of momentum, position, momentum that you can measure. You could also have other observables that aren't combinations of that. Quantum states rho, so that's the classical description. There are also quantum states that we can talk about. So quantum states rho are standard trace 1, trace class operators in the Hilbert space H. So again, these are matrices. These are matrices that act on states in the Hilbert space. And in some sense, they describe the quantum system fully. Yeah, so they are operators on the Hilbert space H of the quantum system Q, and operators on it belong to some operator space, curly O of H. So operators are like mathematical rules that you can apply to things. So an operator might be you multiply whatever your input is by a matrix, or maybe you take the derivative of whatever your input is, whatever it might be. Those are operators. And so there'd be like a family or a space of operators that can act. Is curly O the official term? No, not really. Vectors of the CQ Hilbert space can be thought of as H-valued functions of Z. So typically we think of a quantum state as a vector in a Hilbert space. But if we want to talk about CQ systems, which are classical quantum systems, you also have to incorporate the position momentum stuff of the classical system. So instead of just being a vector in a Hilbert space, meaning meaning something that's H-valued, we actually want it to be a vector in the Hilbert space that changes at different locations in P and Q, for different values of momentum and position. And so they can introduce this map. So you take so essentially you have the quantum operators and you have the classical operators. And I guess they're introducing this updoot. This updoot is, I guess it's like an upcaret or something. And so basically it takes a classical operator, or it takes a quantum operator, that's this guy, and it takes a classical operator, and it mixes them in a way to output another quantum operator. Yeah, okay, so the live is lagging for some reason. I think we're back to normal. So so those will give the classical quantum operators. So a CQ state satisfies the normalization condition that we've already been over, and it generates the reduced quantum and classical states via the formulas that we used earlier. You can either take its trace or you can integrate over it to get the reduced classical and quantum states. For example, this is good. Examples are always good. For example, the state of a hybrid system consisting of classical spatial degrees of freedom and a quantum spin 1/2 is described by a 2x2. So we have a classical like kind of position degree of freedom, so it can like move around, and you have a quantum spin 1/2 system. So you're describing a thing that's quantum in its spin. I hate that like TikTok is having such bad connection. So you're taking something that's quantum in its spin, but classical in its trajectory. And so it's described by a 2x2 matrix. So a 2x2 matrix describes a quantum spin 1/2 thing. But that 2x2 matrix of the entries in the 2x2 matrix are phase space functions. So their values, the entries in the 2x2 matrix, depend on where you are in the classical phase space. Frames dropping, last formula definition missed with description. Okay, yeah, so are you talking about this? So this formula basically tells you how to take a classical operator, a classical measurement, and a quantum measurement, and convert it to a quantum measurement on a classical quantum system. Right, so going back to where we were, so an example would be a quantum spin one-half system that has classical motion. It will be a 2x2 matrix, so a 2x2 matrix describes a quantum spin one-half system, and the entries in the matrix depend on position and momentum. And so then it'll be subject to the certain constraints that we talked about in section 2, that's earlier. So a product form of a CQ state, so you can always write, or maybe not always, so you could express a classical quantum state as a product of the two things. So you have the matrix piece, which comes from the matrix piece, which is kind of like the quantum piece, and the probability piece, which is the classical piece. This describes a normalized quantum state, rho of z and t, that is conditioned on a classical system being in the state z. So you would have a quantum system, and you're describing the quantum system only when the classical system is in a certain state. So that's what this rho of z and t is. And then you can just multiply by the probability of being in that state. So you can do this product form, you can express this product form conditioned on the classical system being in the state z. It does not imply the absence of correlations between observables of the classical and quantum subsystem. So the classical system can affect the quantum subsystem and vice versa. That's what they're saying here. Even if you can express it in product form, that can still happen. Since the Hilbert space operations are the same for Q and CQ objects, so the language that we still use Hilbert space operators. We use the hat only for classical quantum states rho hat to distinguish them from purely quantum states rho. That's the only reason the hat's there. It's just to promote a classical quantum state to a kind of a pure quantum state. So this guy would, so rho hat would live here, and you would get there by plugging in the quantum density matrix that's conditioned on the classical state and then the classical state. So that's okay. That's all of the mathematical background that we're going to need, apparently. So we can actually go to the meat and potatoes now. Where were we? We went to Appendix A. Right, so further mathematical details related to the structure of hybrid systems are provided in Appendix A. Great, okay, we're done with that. So a CP trace remember, CP is completely positive. So I'll just say completely positive because I don't like saying CP. So a completely positive trace decreasing evolution, rho hat of t. Remember, rho hat of t describes the CQ state. This is equal to an evolution operator acting on the original CQ state. This is given explicitly via a kernel. A kernel is an integral operation. Basically, you can integrate you integrate over space, and it tells you how it transforms as a function of time. So this kernel basically is the evolution. So how do I want to describe this? So the kernel tells you how the system evolves at a given moment of time. And so in order to actually compute that, you need to know relations between different points. And so that's why it depends on z and z tilde. Oh, this is a typo. Z and z prime. And so you should integrate over z prime. And you end up with the completely positive trace decreasing evolution of the original CQ state at time 0. If this is true for every time t, so this is just a description, we're saying that if this is a good description of the evolution, then it is generated by the Gorini-Kosakovsky-Sudarshan-Lindblad equation. I've never heard of that, but presumably they're going to explain it. It's just probably originally written down by these people in this reference 8, which can take several forms. So the equation can take several forms. So this is all to say, if this is true, if this is a good description of the evolution of the classical quantum system, then the classical quantum system rho hat, as a function of z and t, has to obey a certain equation. I guess it's called this equation. And so one of the forms that equation takes is this horrible, horrible equation. So let's just read it, and then they're going to explain what the symbols are. So here we have the time derivatives. This tells us how the classical quantum state evolves over time. And so there's going to be a few different pieces. One is going to be a commutator between the between the Hamiltonian, H stands for Hamiltonian here, and the classical quantum systems. This is a commutator. That's how you get to time evolution in traditional quantum mechanics. If this was just pure quantum mechanics, if there's nothing classical happening, then none of these remaining terms would be there. It would just be this. But there is extra classical stuff going on, so we need extra stuff. And then there's, I guess, this coefficient lambda mu nu, which depends on position and time. And then there's some operators that depend on like these operators L mu and L nu, and they act on rho hat. And then there's another commutator with these L mu, L nu things, and this is the plus. I guess this is a certain ordering. And then there's an integral that involves another kernel. It's complicated. Hopefully they'll explain. So here the commutator term, that's this one. Here the commutator term describes unitary Hamiltonian evolution with classical phase space dependence. That's exactly what I said. The second term represents a Lindblad type dissipator that is local in phase space. So that's this term. So this is basically saying that we don't, okay, so since it's not unitary, since it's not reversible, there's like some sort of kind of friction, it's called a dissipator. Think of it like as a sort of friction that kind of like spreads out or smears out the evolution over time. And that can happen for, multiple reasons. That can just happen as a result of the evolution. You can just impose that that's a thing that can happen. If it wouldn't happen, then it could be that these quantities are zero. But we have to allow for it to happen in these kinds of completely positive time evolutions. So that's what the second term does. It's a Lindblad type dissipator that is local in phase space, so it only depends at a particular point in phase space. And the integral term, which is this one here, the integral term introduces non-local couplings across classical configurations. So you could have like an effect that depends on one particular configuration could affect some other particular configuration. I guess having non-local couplings is allowed because it doesn't transmit information here. The anti-commutator, which I guess is, okay, these are anti-commutators. The anti-commutator of two operators is defined as a comma b plus, and it's AB, so A and B, you can think of them as matrices. So you do A times B plus B times A. It's not the same thing if A and B are both matrices. So that's what these mean. So you take L dagger nu, L mu, and you take the anti-commutator with rho hat, and then you do the same thing here. So these are just introducing basically two different, so these are local dissipations, and these are non-local dissipations. Fine. Because notice that these have the same form. This guy and this guy, and this guy and this guy. They're roughly the same. It's just one is local because it depends on, who's at my house? Because it depends on multiple different positions. Just showed up and ran away. Sorry, one sec. One sec. No one was at the door. Weird. But okay. I mean, like I saw a person like walking up because my window's like right here, but weird. Right, okay. So we have local and we have non-local dissipation type terms. So, and we have this kernel here, which is just an integral over. Yeah. So the kernel is just this guy on its own, integrated over z prime. Right, and that multiplies the kernel that multiplies the last term has been absorbed into the integral. Fine, because this needs to depend on. Yeah. Okay. So we need to explain what L is. So L mu is a basis set of operators that we assume to be Hilbert-Schmidt orthogonal. So it's just like a family of operators, right? That's all it is. It's just a family of operators that have a certain property and thus span the space of all trace class operators. In general, we use the set of operators L mu is L naught and L alpha. That includes the identity operator on the Hilbert space H. So L naught is the identity operator, and then L alpha is just other things. So the point is there's just this coefficient, lambda mu nu. That's just saying that you can have any combination of these depending on what the dynamics are. That would tell you something about how the dissipation behaves. Here and in what follows, we use the Einstein convention to sum over repeated indices. Yeah, I should have been clear there. That's intuitive to me, but not super clear to other people. When you have repeated upstairs indices and downstairs indices, so this term, you have an upstairs mu and a downstairs mu, and an upstairs nu and a downstairs nu. That means that you're adding up, ranging from 0 to whatever the final number is, for all values of mu and nu. So this is actually like a whole bunch of different terms added together. It's just a, like you can imagine having like the summation notation in front of this, and then you're summing up all of the values of mu and nu. This is an Einstein thing. Right, for continuous bases, the sum over mu nu is replaced by an integral. Yeah, so in principle, you could have a continuous, oh, I missed a sentence. For finite dimensional spaces of dimension d, it is convenient to choose L alpha as the set of generators of SUD. So the point is if your Hilbert space is finite dimensional, then L mu is also finite dimensional because there's only a finite number of operators that form a basis. And so you can just write them down. They are the generators of SUD, which is a Lie group, special unitary group of dimension D. Don't worry about that. These are basically just different matrices that can describe different combinations of like the kinds of measurements that you can make. Right, and then alternatively, you could have infinitely many operators or an infinite dimensional operator space, and you could even have like a continuously infinite dimensional operator space. And so you would just replace the summation over all of the indices, 1 to 5 if it was finite dimensional, you would replace by an integral. The coefficients lambda mu nu characterize the strength of various non-Hamiltonian terms. Yeah, that's all it is. It's just you have the Hamiltonian bit that tells you unitary evolution, and this tells you all of the rest of the stuff. I mean, presumably they're going to explain W as well. Oh, actually, yeah. The probability is conserved. So that's good. It means that the total probability at any one place stays the same. Oh, wait a minute, hold on. Yeah, so keep in mind, remember that this guy, if you integrate over the z's, you get the quantum state. And so this is saying that the probability of being in any particular quantum state is unchanged. That's what it means for its time derivative to be 0. So that's kind of a good thing. And the matrices lambda mu nu, W mu nu, and lambda mu nu plus W mu nu, they satisfy the positive semi-definiteness requirements. These are just technical mathematical requirements to make sure that the axioms that we talked about at the beginning are obeyed. Okay. So this is the kind of the equation that we're interested in, because this tells us how the classical quantum system changes over time, right? In fact, so much so that they call it the master equation. So this form of the master equation explicitly separates the Hamiltonian and the stochastic parts, which allows for an easy reduction to purely classical and purely quantum cases. Following reference 6, we consider only the autonomous case, where there is no time dependence in lambda mu nu and W mu nu. So this is the case where kind of the dissipative, the non-Hamiltonian behavior doesn't change in time, right? That's sort of relevant because otherwise it gets really, really complicated. Then the dynamics is generated by the Liouvillean superoperator L, which acts on the operator valued function rho hat of T and Z as follows. So the dynamics tells you how the things change, which is represented by this guy. And so they're kind of repackaging it into this Liouvillean superoperator L. So this is an operator that acts on another operator. That's why it's a superoperator. And it tells you what the time dependence is of your classical quantum state operator. Or put another way, you can kind of solve this system. It's a first order differential equation. It is the exponential of the Liouvillean operator times the time parameter t acting on the original classical quantum state. Okay, so this is the formula that you can use. Oh, and this is kind of nifty. You can actually repackage this evolution in terms of an integral equation. So you can write this integral as h. So they're just repackaging this equation here in like a cleaner form, right? And if you do that, then you just get one integral and one anticommutator. And the amplitudes, the amplitudes both in the integral and the anticommutator, they're built from the decomposition of the Hamiltonian, which is this guy. So basically, they're just repackaging all of the variables here. Congrats, Adam. Congrats on getting into the U of University of Manchester. That's big. Yeah, so it's just repackaged this way because it's nice and clean. Right. Now, how much more of this technical stuff do we have? Okay, not much more. Good. Because I know the technical stuff is really hard to get through. But we have to do it because we have to understand what's being done. So, now we have to talk about statistical moments. So it's useful to define nth statistical moments, d mu nu subscript n, of the amplitudes h mu nu. So these are amplitudes. They tell you essentially the evolution between one classical point and another classical point. So these are statistical moments. Statistical moments are basically the integral of something times, well, let me give another example. Actually, let me just pull up an example. Probability distribution. There might be some pictures that I can give. Let's see. This is sort of helpful. So essentially, for a probability distribution, a moment essentially characterizes kind of the shape of the probability distribution. So, for example, the first moment of a probability distribution tells you what the average of the probability distribution is, what the average outcome is of the probability of whatever has various probabilities. So if you just pick them over and over again at random, it would tell you what the average result is. The second moment tells you something about how like lopsided the probability distribution is away from that average. The third one tells you even more information, and so on. So they want the statistical moments of these amplitudes, because these amplitudes in some sense connect. They tell you how the classical quantum states are related, or they tell you about the probability of being in a certain classical quantum state. They give you information about that. Gives you information about how the classical quantum state changes. So you'd want to know how it's distributed. So you can define these. D mu nu, so the nth statistical moment, the way that you compute statistical moments in the classical probability way, the first moment is if your probability distribution is, say, y of x, where x is the various outcomes and y is the probability, then the first moment would be y times your probability density function. Sorry, it would be x times your probability density function. Your second moment would be x squared times your probability density function. Your third moment would be x cubed, and so on and so forth. So the nth statistical moment here is just, well, you're integrating over z minus z prime n number of times. So this is just a normal statistical moment, just kind of generalized to this broader context. Sorry, I'm taking off my jacket. It's a bit warm in here. So in fact, then we can actually. Sorry, I just want to hang up my jacket. In fact, then we can rewrite h in terms of these statistical moments, because this is a thing that you can do. Essentially, by taking derivatives of these guys and adding them up, you can get h back. So then you can rewrite your master equation this way, and this is now in terms of statistical moments. So here we're summing over from 1 to n. So here we're going to have a contribution from the statistical moments. Then we have the Hamiltonian evolution. And then we have some 0th order statistical moments. And then we have some non-zeroth order statistical moments, which gets rid of all of the integrals, essentially. They're kind of packaged in the statistical moments, and these are things that could be like measured or characterized in some nice way. So, and h hat here, where's h hat? They probably meant to put h hat here. H hat is this guy. Right, and they're going to explain it again, which is nice. The first line of this equation represents the purely classical dynamics. So this is the purely classical piece. That's good. It's described by the moments d0, 0, generated by the quantum identity components of the evolution. So remember, when mu and nu are 0, the operator, they say it over here, the operator is the identity. So it just doesn't do anything to the quantum stuff, and it'll only do stuff to the classical things, to the classical piece. So D00 generated by the quantum identity component of the evolution. So this is just a classical piece. The second line is the GKSL evolution controlled by the classical state, or controlled by the classical state Z in B. That's this whole thing. So that's the evolution of the quantum state. That's all of, like, well, it's the evolution, it's the dissipative evolution of the quantum state. And because the probability isn't changing in the quantum system except for dissipation, that's fine. And then the last line represents the quantum back reaction on the classical system. So in particular, you can have the... Yeah, so this is the full classical quantum state. This is the full classical quantum state. This is the purely quantum state. And so this purely quantum state, this is going to contribute some to the evolution of the classical quantum system, the whole classical quantum system. So that's why they're saying that the last system is the quantum back reaction of the classical system. Oh, from Suno Peak. Okay, but what if you divide by 0 after applying L'Hopital while integrating to the third? Okay, good meme. Good meme. I don't know what AED50 is, but thank you. By the way, if you like what I'm doing here, if you like seeing the peer reviews, contributing to my live stream, whether via donations or likes or subscribes or shares, these are all ways to convince me that these are worthwhile, right? Yeah, right. So the last line represents the quantum back reaction on the classical system. Great. Particularly important are the first order moments that can be interpreted as forces exerted by the classical system Q on the classical system C, and the second order moments describing the phase space diffusion. So that's actually a really interesting point. So if you look at the first order moments, those are going to be the ones that have d with a subscript 1. I guess apparently that will correspond to a force. And I guess that kind of makes sense, right? Because you have a classical system, so the force depends on the classical system. And so what we're seeing is that the rate of change of the quantums of the full system will depend on one time derivative. Hold on, does this check out? This is a sum, not a... Hold on, let me make sense of this. Why would the second one correspond to a phase space diffusion? We can think about that. But apparently, and maybe once they do an example, it'll be a little bit more clear. But apparently the first order moments, the ones where n is 1, so that's the first element in the sum, those can be interpreted as forces, and then the second order moments, when n is 2, those can be described by phase space diffusion, meaning that it's kind of like smearing out your whole, your probability is kind of getting more and more diffuse. So, oh, and then we can compute some expectation values, and apparently they'll tell us something. So the 3 expectation values, remember, expectation values are the averages of a bunch of measurements of a certain quantity. So D0, wait, how are we defining D0? Okay, this is just a definition. So the defining D0, this is the trace of, so L is the operator that, wait, hold on, so let's think about this. So D are the moment, the D's are the moments, D's nuts. The D's are the moments of the evolution operator, sorry, they're the moments that describe the amplitude that describes the evolution operator. And the L's tell you about the, and they capture kind of all of the evolution except the Hamiltonian stuff. And the L's are the possible ways that you could have diffusion or forces, basically all of the possible things that you could do to your system. And so this is saying that there is some piece of the evolution, which is all of the pieces added together. That's what it is. So this is all of the possible forces and interactions added together that are, that just contribute to the probability here. Remember, you're taking the trace, and yeah, so this is just the probability of a certain state. Sorry, let me back up. For a certain type of evolution, this is the probability that you would expect. Hold on, let's make sense of this. So this tells you this is an evolution operator of a certain kind. So it'll tell you evolution for a certain specification of the system, right? And then this just tells you how it evolves. Now, if you evolve your system in the... Yeah, so what does D0 do? D0, okay, so D0, sorry. Okay, the second line is the GKSL evolution controlled by the classical state and is determined by the 0th order moments. So these are the 0th order moments. This tells us something about the evolution of the classical state. This will tell us something about the evolution of, or the effect of the quantum state on the classical state. That's why it's called back reaction 1, and this will tell us the effect of the quantum state on the classical state, but the second order terms, the diffusive terms. So that's why they call it back reaction 2. These are of particular relevance for encoding the back reaction of the quantum system onto the classical background. More specifically, the necessary condition for classical quantum dynamics with quantum back reaction is that D0 has to be greater than 0. In addition, the moments have to satisfy the diffusion decoherence relation. So apparently, one can prove that if you take the product of the first and the last, and you multiply it by 2, it has to be bigger than twice. It has to be bigger than the square of the first one. I guess this is sort of constraining the type of evolutions that you have of your quantum system. So I don't really understand that, but I imagine that in the example, because they are going to run through an example, I imagine that they'll explain these in detail. So let's just hold up on our confusion for a while. It's often the case that they explain something generally and then do something more specifically, which explains what's going on. So I guess they're now going to talk about fundamental issues. I just want to make sure that they're actually going to work out the example. Okay, so that's in section 4. So let's read about the fundamental issues first. Okay. Fundamental issues arising from a completely positive evolution. Remember, completely positive means that it's a normal evolution, but it allows for dissipation, it allows for kind of smearing, it allows for irreversible processes. One sec. Oops, audio is off. I'll start over. So the consistency requirements imposed on CQ hybrid systems are summarized in Appendix A2. We've already read Appendix A2, so if you're watching on YouTube, you can kind of rewind and go back to where we were doing that. If you're watching on TikTok, go to YouTube, pull up the stream, rewind, you'll find it there. Anyway, there are two distinct types of consistency requirements. The majority deal with formal mathematical or structural properties, such as positivity of classical and quantum probabilities, implementation of canonical transformations, and the classical limit of the quantum and hybrid CQ systems. These are requirements 1 through 4, 6, and 7. The remainder, which is just one of them, requirement 5, conserves consistency with the laws of nature, such as energy conservation laws and the second law of thermodynamics. So yeah, so most of them are just kind of like mathematical stuff to make sure that everything works out. The last requirement is like laws of physics. So for a hybrid model that is used as a computational tool where both subsystems are in fact quantum, but one is treated classically for efficiency, violation of these requirements at some point in the evolution simply sets the timescale over which the scheme remains valid. So generally speaking, if you're just doing this for convenience, which some people do apparently, then you just don't worry about some of these axioms sometimes. In contrast, the same conditions are interpreted much more stringently for hybrid models that purport to be a fundamental theory. There is no expiration date on the formal and structural requirements, and this is precisely where unitary models without additional dissipation and diffusion terms generally fail. The scheme proposed in reference 6, on the other hand, satisfies them by construction. Sure. So consistency with the laws of nature, or more precisely, violation of these laws, to an extent amenable to experimental verification, is a way to falsify such a candidate theory. In a completely positive hybrid model, applied to gravity interacting with quantum matter, information loss is a predetermined outcome. So I guess it's just the case that if you have a hybrid model that applies to gravity, to quantum stuff, then we actually expect one of the laws of nature in information conservation to just be violated. However, it also leads to a violation of energy conservation in a setting where this concept is perfectly well defined. So, in fact, it just says that energy is not conserved, which would be very weird. Not necessarily ruled out, but very weird. Unruh and Wald argued that such violations are unobservable for astrophysical scale black holes. Yeah, that's possible that the violation of energy conservation is just small enough that we haven't seen it yet. The state of the classical system can be represented as a diagonal quantum state. Okay, we have some thinking to do. So the state of the classical system can be represented as a diagonal quantum state of a fictitious system whose Hilbert space is built on B as the configuration space. So you start with a configuration space B, a classical space. You quantize it, but then the classical system is just a diagonal quantum state. So it would just be rather than having any entanglement, it's just diagonal. And what diagonal means is it's basically there's no quantum properties to it. So you can kind of write a classical thing as a quantum thing using the same language. This kind of description with a preferred pointer basis must be supplemented by efficient decoherence that maintains it despite the interactions. A pointer basis is basically kind of the classical degrees of freedom that we want to be like observable things. So think of like when you measure a quantum system, you have like a dial that points to a certain value depending on what the measurement is. The pointer basis is the description of the form where the quantum state is diagonal. It's the basis. How do I want to describe this? So it's basically a set of vectors that point towards different states. And we say that it's a pointer basis if those states correspond to some like observable thing in a laboratory. And then we say that the classical system that is represented in this quantum way is basically just a linear combination of the squares of those basis vectors, kind of an outer product. But that description apparently must also be supplemented by efficient decoherence that maintains the pointer basis despite the interactions. That makes it a bit messy, but basically you just have to make sure that there's a good way to turn the quantum system, which is actually a classical system, back into a classical system. That's what the efficient decoherence does. And it has to maintain those it has to maintain being a diagonal quantum state with a on the preferred pointer basis of vectors. So that's what's being mentioned here. I don't know why this is relevant though, but maybe they'll talk about it. Such a quantum system cannot mediate entanglement because it's classical, and thus the empirical detection of gravity-mediated entanglement would apparently falsify this hybrid scheme. Yeah, so this is saying that if you can actually convey entanglement, if you can actually like kind of cause entanglement by gravitational interactions, then that means that you can't have your gravity system being described by like this classical quantum hybrid thing. That's what the point was here. And so I guess that would just like empirically rule it out if you detected gravity-mediated entanglement. A CQ hybrid theory should also be internally consistent. Positivity requirements ultimately translate into relations such as equation 2.16. So this, I guess, comes from probabilities being the probability of something should always be positive. And so I guess if you calculate probabilities and demand that it's always positive, this is one of the consistency conditions that you get. Which are responsible for the trade-off between dissipation and diffusion. However, the coefficients dn for n equals 0 and 1 are determined by the standard equations of general relativity. For example, Hamiltonian evolution in pure gravity, such as the propagation of gravitational waves in vacuum, and the unitary evolution of quantum fields on a fixed background. So I guess if you're doing this in the gravity setting, then n0 is general relativity, and n1 is the unitary evolution of quantum fields on a fixed background. Therefore, the consistency of such relations with the underlying theory should be analyzed separately. Okay, that's fine. The violation of energy conservation is not the only potentially problematic consequence resulting from the completely positive description of a fundamental theory. Since the evolution under, remember this is the evolution operator, e to the lt, is no longer unitary, the possible trajectories of rho hat of t, so rho hat of t, remember that tells you the entire system. It's a complete description of the system. The possible trajectories of rho hat of t and the asymptotic states, so that means that the behavior after a very, very long time, are determined by possibly degenerate eigenvalues of L. In terms of, so they're going to explain why that's relevant. In terms of their physical significance, one distinguishes 4 types of eigenvalues of L. So L is the evolution operator. So eigenvalues of L, in some sense, will tell you something about energy, because energy and evolution are related. So there are 4 types of eigenvalues. So 0 eigenvalues correspond to stationary states, where we have suppressed the degeneracy levels for the moment. So these are states that just don't change, regardless of how much time passes. Purely imaginary eigenvalues correspond to circular paths, meaning that there are starting configurations that will not approach an equilibrium state in the long time limit. So these are states that will kind of oscillate between 2 states or oscillate between 3 states or whatever. However, they appear only under very restrictive conditions that are typically not realized in physically relevant situations. Okay, that's good, because if there's no like long-term behavior, then that'd be very confusing. Lastly, real negative eigenvalues directly lead to 0. So that is to say, if the eigenvalues of L are negative real numbers, then that means that e to the minus a number times t, when in the large T limit, would just take you to 0 as t goes to infinity. Yeah, so real negative eigenvalues directly lead to 0, while complex pairs of eigenvalues with negative real parts spiral to 0. So this is to say that you can have states kind of just disappear if they have negative eigenvalues. The set of asymptotic states rho hat infinity forms an asymptotic subspace. I guess it's called AS of H of the state space. So yeah, the point is that some states can just go to 0 if they have negative eigenvalues. So your final states, the states after you wait a very, very long time of evolution. So imagine that you have a classical quantum state in some initial configuration, and you just let it go for a while. We're interested in what the end result looks like after waiting a long time. That's what the asymptotic states are. And the point is that even if you start with some states, it's possible that those states just go away and they can never contribute because they might have negative eigenvalues of L. And that's kind of really weird. The set of asymptotic states rho hat infinity forms an asymptotic subspace. So it's a subspace, it's not the whole thing, because some of them can go to 0 of the state space. It attracts all initial states and is free from decoherence. So every starting state ends up in this final subspace of possible asymptotic states. Any remaining time evolution within AS of H is unitary, meaning once you're in this asymptotic subspace, everything just behaves in a reversible way. Basically, nothing really changes. It's reversible thermodynamically. Okay, for a large number of systems, particularly finite dimensional ones, the steady state is unique. Okay, that's cool. That there's only one possible end state. In any case, AS of H is generically a proper subspace of the state space, and the generic initial condition. So, by the way, this means that there will for sufficiently general systems, sufficiently general time evolutions, there will be states that have negative eigenvalues for L, meaning that those states will not contribute to the final possible states. That's why it says it's a proper subspace of the state space. And a generic initial condition, rho hat of t equals 0, asymptotically evolves into a block diagonal form. So you'll have basically a sum of entangled states. Several results describe how particular initial states are mapped into such blocks, also known as basins. Okay, that's neat. Right, okay. I guess there's important consequences. This has important consequences for conservation laws. In a quantum system that evolves unitarily, that means that it's in a reversible way, a time-independent self-adjoint operator A, so time-independent means it doesn't change in time, self-adjoint means that it corresponds to a measurement. A time-independent self-adjoint operator A, okay, it doesn't exactly correspond to a measurement, but it's close, represents a conserved observable if and only if it commutes with the system's Hamiltonian H. So essentially, if you have something that you want to be a conserved quantity, like momentum or energy or angular momentum or whatever, you need to have a time-independent self-adjoint operator A that commutes with the Hamiltonian. That's normal quantum mechanics. That's how you know when there's a conserved quantity. Analogously, for a classical phase space function, the conservation is equivalent to the vanishing of the Poisson bracket with the Hamiltonian. Remember the Poisson bracket I mentioned at the very beginning? That's what's happening here. That's like it's kind of analogous to the commutator. According to Noether's theorem, which is how we relate symmetries to conserved quantities, continuous symmetries of the Lagrangian result in conserved quantities. That's a whole big deal. That was like the driving force behind classical physics. Really, physics in general was Noether's theorem of like modern classical physics, because basically you can write things in terms of Lagrangians, which is like a kind of a way of examining the trajectories of classical systems and then studying the way that those trajectories kind of behave. Um, when you're Lagrangian, which is like a number basically, when your Lagrangian doesn't change, when you do certain things, these are continuous symmetries to your underlying system, then that means that there's a conserved quantity associated with that transformation, with that continuous transformation. That's what Noether's theorem states. In Hamiltonian systems, these conserved quantities typically serve as generators of the associated symmetry transformations. So the conserved quantities, like momentum, you can then apply the Legendre transformation to these various conserved quantities, and you get generators. So these would now be transformations themselves, and they generate the symmetries. These are in Hamiltonian systems. So in table 1 provides an overview of local and global conservation laws, as well as the applicability of Noether's theorem in different theoretical frameworks. Let's go look at table 1 really quick. It's going to be very small, so let's just read these really quick and then we can scroll. So if we're in classical mechanics, a symmetry of the symmetries of equations of motions can have symmetries. There won't be local conservation of energy of anything, because that's not really well defined. There will be global conservation, which means that the total energy of the system is conserved. And Noether's theorem applies. In classical field theory, so that's like for like a bowling ball being shot through the air. Like you'll have some symmetry that implies global conservation of energy or momentum or something. Classical field theory will have a symmetry. If you have a symmetry of the equations of motion, then you will get local conservation laws. And you'll get, so local conservation laws are like, if you have a certain amount of energy here at this moment in time, then the amount of energy at that moment, then the amount of energy at that place at a later moment in time is equal to the amount of energy that there was before, plus the amount of energy that came in, minus the amount of energy that left. That's what a local conservation law is like. But it will also conserve things globally, so there will be like a total momentum that is unchanging. And that comes from Noether's theorem. We have quantum mechanics, closed quantum mechanical systems. Symmetries of the equations of motion can exist. There again is no local conservation, kind of like the classical mechanics. There's no, it just doesn't mean anything. You do still have global conservation laws. You do still have Noether's theorem. If you have open quantum systems, these are systems that have like some sort of dissipation effects. You can still have symmetries of the equations of motion, but you don't get local conservation laws because you get decoherence, you get dissipation. You don't get global conservation because you can have energy leaking out. That's what dissipation is. And you don't get Noether's theorem. Noether's theorem doesn't hold. Similarly, in general relativity, you can have symmetries of the equations of motion. There's a lot of them, infinitely many even. You can have local conservation. There is no globally defined conservation of, say, energy. And there is no Noether's theorem in general relativity. Not really, anyway. Quantum field theory, we have symmetries of the equations of motion. That's fine. We can have local conservation. That's also fine. We can have global conservation. We can have global conservation if there are no quantum anomalies. And we can have Noether's theorem if there are no quantum anomalies. Don't worry about what a quantum anomaly is. It's complicated. In quantum field theory, in curved spacetimes, it gets even more complicated. You may or may not have symmetries of equations of motion. That depends on what your curved spacetime is doing. You may or may not have local conservation because that depends on anomalies. It's really, really annoying. There's something called a trace anomaly. You definitely don't get global conservation because in curved spacetimes there's generally just not any killing vectors, and killing vectors are the things that give rise to global conservations or global conserved quantities, and there's no Noether's theorem either because you have a trace anomaly. So quantum field theory in curved spacetime, one of my projects is doing quantum field theory in curved spacetime. It's really hard. And then we have classical quantum hybrid models. This is what we're talking about. You do have symmetries of the equations of motion. You don't have continuity equations, so that you don't get local conservation of anything in general. You don't get global symmetries or global conservations, and there's no global action. So there's just a lot that's missing if we're doing classical quantum hybrid models, which is just really, really bad. Really, really ill-behaved. But we can still do something, right? Sorry, I'm gonna drink some water. One moment. Ooh, my tummy's rumbly. Must mean I'm hungry because I woke up early. For systems with completely positive dynamics, the conservation of such an observable, remember, an observable is just one of these things, A. The conservation of such an observable naturally means that that observable doesn't change in time, and that means that the evolution, the time evolution of the observable is 0. Remember, L is the time evolution operator. As a result, the relation between symmetries and conserved quantities established by Noether's theorem is broken. Because Noether's theorem isn't really related to... Noether's theorem is related to actions, but there's no actions, symmetries, and stuff like that happening here. On the other hand, is my guess, on the one hand, there may exist conserved quantities that do not commute with every term in L. Meaning that you take your conserved quantity, you commute it with L. If it, in normal, like typical quantum mechanics, you would expect that that means that the commutator should be 0, but it doesn't have to be. It doesn't have to be where L generates time evolution. So there may exist conserved quantities that do not commute with every term in L. Consequently, not all unitary transformations that such observables generate are symmetries of the system. So it's not necessarily the case that a conserved quantity is associated with a transformation of the system that leaves the system unchanged, which is weird. On the other hand, a symmetry generator does not have to be a conserved quantity. In the following section, we present an example of a rotationally invariant CQ system which does not conserve its angular momentum. Okay, this is going to be good. Examples are good. Apart from t going to infinity asymptotics, other timescales may be important. Due to the splitting of the spectrum of L, a partial relaxation into long-lived metastable states is possible. So you could have like a system that like evolves into like a long-lived state, but it's not quite asymptotically stable. It'll eventually decay into something else. These are distinct from the asymptotic stationary states, rho infinity. Metastability manifests itself as mid or long time regime when the system appears stationary before eventually approaching the asymptotic space. For specific models, it's possible to obtain a low-dimensional approximation of the dynamics in terms of the motion of the manifold of metastable states. So essentially, rather than working out the whole dynamics of the whole system, which could be really complicated, instead you just break it up into there's different metastable states that the state will always be in, or some combination of them, and then those metastable states evolve together. And that's kind of like an approximation of the whole thing. The separation between the low-lying eigenvalues and the rest of the spectrum occurs at some lambda m, where the real part of lambda m is much, much, much greater than the real part of lambda m minus 1. So basically, the spectrum, meaning the eigenvalues of curly L, those eigenvalues, well, you can order them in terms of how big their real part is. And if the real part is very, very small, if the absolute value of the real part is very, very small, I should say, that means that the state evolves very, very slowly. And so there will be some real parts that are very, very small, some that are very, very big, some that are in the middle. And so essentially you can kind of split them between the ones that live for a long time, which have very, very small real parts, and the ones that don't. And so then the upper limit on the duration of the metastable interval, which is how long the long-lived states live, is then determined by 1 divided by the real part of the eigenvalue. So if the eigenvalue has a very, very small real part, whether it's positive or negative, that means that it lives for a long time. So 1 divided by a small thing is a big thing. Right. Okay, let's do the toy model, because this will hopefully make everything much easier. It's very low dimensional. Everything should be very explicit. And how much do we have left? Oh, we only have like a page and a half. Cool. Okay. So Noether's theorem does not apply in CQ frameworks due to the lack of a unified action principle that treats both classical and quantum components on an equal footing. Yeah, that seems like a real problem. So we can't use Noether's theorem to talk about conserved things. While this does not a priori preclude the possibility that symmetry generators are conserved, it implies that their conservation cannot be derived using traditional, i.e. based on global action-based symmetry principles, traditional variational and/or symplectic methods. In this section, we study a simple toy model to illustrate that angular momentum is not conserved under the dynamical evolution prescribed by the master equation. So for those who are asking, Noether's theorem tells you that there's a relationship between conserved quantities like energy and momentum and angular momentum, and symmetries or ways that the system that you're studying is unchanged when you change it, when you apply a certain transformation to it. Right. So, okay, let's do the example. Consider a qubit interacting with a classical particle in 3+1 dimensions. So a qubit is just a thing that's either spin up or spin down. And then there's a classical particle, which is just a thing that moves, has an XYZ coordinate, has speed, has momentum, all these things. According to equation 2.5, this guy, this big, long, horrible one, but I guess they're going to do it explicitly, so it shouldn't be so bad. According to equation 2.5, the dynamics of this coupled system is described by this equation. We got to zoom out a little bit. But this actually isn't so bad. There's only a few terms. So we have the rate of, so let's go look at this equation and see if we can derive it. So we have the Hamiltonian evolution, which there is no Hamiltonian evolution in our situation. There is no quantum Hamiltonian evolution. The Hamiltonian operator, I guess, is probably just 0. So this term 0. So there's only going to be these terms. There's going to be the local Lindblad type dissipator, and then there's the non-local dissipator. At least I think that that's what they're doing. Yeah, so let's just double check. Yeah, I think that so the Hamiltonian that they have is just 0 here. So if the quantum system were just on its own, nothing would happen. Because there would be no quantum or time evolution. That's why there's no commutator here. But you can have this first term. So we have to, so keep in mind that this is the Hilbert space. The Hilbert space for a two-dimensional, the Hilbert space for a single qubit is 4-dimensional, right? 3-dimensional, 4-dimensional. It's low dimensional. You have the identity operator, and then so the point is that these L's that could appear, there's just not very many of them. So that's why there's only one term here. So actually this should be a matrix. So it shouldn't just be a multiple. It shouldn't just be a multiplier. So why are they getting a multiplier? Oh no, that is a matrix. Okay, that's just a matrix product. That's fine. So they've just expressed this as a matrix product. Fine. This term is just a matrix product on rho hat. And then they've expressed the second term, the integral term. Oh, I think that they're actually using this formulation, right? Are they? They said that they're using equation 2.5. How did they get this? Where did this come from? Let's think a little bit carefully. So we could have this term, but we have good reason to think the Hamiltonian is 0. So that term is just 0. Fine. Now, the space of operators. So we have. Yeah, so what's the space of operators on a single qubit? So I guess the space of operators you could either... No, the space of operators is 2-dimensional. That's why. Okay. The space of operators is 2-dimensional. You can either take the qubit and leave it alone, or you can flip the qubit. And then you can take combinations of the two. But those two things are going to be equivalent, right? Yeah, and then you can just take linear combinations. You could take complex linear combinations, so that should be it. And so that means... Well, but wait a minute then. So if we wanted to be extra rigorous and double check this, what we would do is we would check that these two expressions, regardless of what lambda is, these two expressions can be written as a single matrix times the density operator, because your space of bases, or because your basis set is only has 2 elements. So if that's true, then you can express that first term just in terms of a single matrix multiplication. And then we can go look at the second term. So the second term is going to have a few different contributions. So it will have, I guess, this is a weird way that they did this. So they write the final state of the combined CQ system. So rho F is the final state of the combined CQ system, and then they're multiplying it by an integral, and they have the dissipation again. They're multiplying it by the integral of the CQ system plus the Pauli matrices. Oh, no, I'm stupid. No, the Pauli matrices make up the basis for the operators that can act. So there's definitely three of them, not just one. So this is the where is it? This is this term here. So it's this guy. This guy is just 0, I guess. And so they have L mu rho hat L nu summed over all of the appropriate things. So here they have sigma A, and they're just saying that the dissipation, the W, is just 1. This is just the function 1 for all of its indices. Sorry, it's not the function 1. It's this function here. It's the final state times the dissipation rate. Now, it's not clear why they're setting that to be the... Okay, no, that actually does make sense. If they wanted to kind of dissipate uniformly, so that it dissipates into a whole bunch of different states, then you would just weight them all equally. So it would stay, so you could have essentially kind of the most symmetric type of dissipation. So you would set W to 1 and you'd set lambda to 1. Now, if you set lambda to 1, the question is does this and do these guys give you just kappa? Sorry, if you set W to kappa and lambda to kappa, do these guys just give you kappa times the original thing? That's the question. I don't fully understand that, but let's just go with it and see how it goes. So here we have to zoom a little bit. So here A is in XYZ, yeah, so we have sigma X, sigma Y, and sigma Z, no problem there. Kappa corresponds to the decoherence rate, so that's what's happening here. We have decoherence of the system, and then we also have the decoherence affecting kind of the mixing of the system. And rho sub F is the final state of the combined CQ system. They have a footnote here. Note that the magnitude of P, so that's how far away you are from the origin, how big your momentum is, and the dot product. This is just, you have a vector for your position, a vector for your momentum, you take the product of the two. Those three things form apparently a minimally rotationally invariant set of scalars that fully characterize the dependence of rho F on classical variables. Fine. The origin of the system. So this is just a classical system. It's going to have an origin of its coordinate system. So apparently, I don't know, I have no idea how they did this. Apparently you can just write down the solution to this differential equation, because this is a differential equation, right? This tells you that how rho hat changes with time. And, you know, there's this piece, which if that was all that there is, it would be pretty trivial to solve. But there's also this piece, which is an integral over rho hat. So I have no idea how, well, okay, I guess that the t dependence doesn't show up there, but apparently you can just write down the solution. I have no idea how they do that, but apparently you can. But the solution looks like the leading term. So if you just had this, then you would just get this term. And then there's all of the rest of it. So you have a term that looks like 1 minus this term. That depends on the final solution. So you have the initial final solution. So you have the initial solution that evolves and kind of just decays away with time. And you have the final solution, the solution at a late time. The final state, I should say, not final solution. The final state, so the initial state decays away. The final state starts existing at a rate inversely, like that's kind of inverse to the decay of the initial state. And then between the initial and final state, you have all of this stuff happening. And so so this is just the extra contribution from the quantum system on the classical system. So that's the solution to the differential equation. And now I guess they're going to simplify. So if we use the normalization 2.3, 2.3 is just that this equation has to hold. And then we also have this identity. This is just an identity relating the Pauli matrices. That's the sigma x, y, and z are, and some matrix rho hat. That's equal to twice times the trace of the matrix times the identity matrix. So this is just this is just like kind of an algebraic identity. It's like saying that x squared is equal to x. It's like saying that 3 squared is equal to 3 plus 3 plus 3 or something like that. So it's an algebraic identity. Then this solution, which is here, equation 4.2, it simplifies a lot, which is really nice. I guess all of these terms just go away. Oh, well, no, they don't go away. Sorry, they contribute exactly this. And so what we're left with is this as our solution. We start with the initial state, which decays away, and then we add to it the final state, which grows. Now, let's just be a little bit careful and think about this. No, that's actually fine. So now they're actually just going to specify what the initial condition is. So here we have the initial state, and then the final state ends up mapping onto the identity. So it ends up being an equal combination. So I should be specific here. So the matrix part of this whole system, the matrix part, the row part, basically that's telling you what your spin state is. You're either spin up or spin down, or some linear combination of them, or some superposition of them, or whatever. So what we're saying is that regardless of what initial state you start in, if you take the t goes to infinity limit, so take t goes to infinity, you'll end up with the particle being at some place, and then the spin is going to be in an equal statistical combination of spin up and spin down, regardless of what your initial spin is, because of this kind of back reaction between the spin and the classical position. And we know that that's the case because this I hat is the classical this I hat, that's the identity operator, which means it has a 1, it's a 2 by 2 matrix, which has a 1 in the top left corner and a 1 in the bottom right corner. And so that corresponds to a classical superposition. Sorry, not a classical superposition, a classical statistical combination of spin up and spin down. Meaning not that it's in some weird quantum superposition, but just that it has a 50-50 chance of being spin up and spin down. There's nothing spooky happening if you wait a long time. Now, they're actually going to work out the explicit details, I guess, which is kind of nice. So let us now suppose that the initial state is given by this. So initially, the particle will be at some position, Q naught. It will be at, how is superposition different from 50-50? Superposition can self-interfere. 50-50 cannot. That's the difference. It's a mixed state. It starts with an initial position, an initial momentum, and then it starts in some initial spin configuration, where rho hat I is a constant density matrix. So this is it's just a density matrix that tells you the initial condition. The initial orbital angular momentum. So we have a classical particle, so there's going to be two pieces of angular momentum, right? There's going to be the angular momentum from the quantum spin system, spin up or spin down, and then there's going to be angular momentum from just like the motion of the particle. Like if the particle is moving in a circle, then like that will give you the orbital angular momentum, and you have to add the two. So the initial orbital angular momentum is just Q naught cross product with P naught. That's the formula for the initial spin, or for the orbital angular momentum. And the initial spin operator expectation values are this. So we can just compute what the expectation values are for the initial spin. So it's just h bar over 2, that's the Planck constant, divided by 2, times the average of the spin operator acting on our initial state. So this is like, what is the average spin in the x direction? What's the average spin in the y direction? What's the average spin in the z direction? That's how you compute this, if you were to measure it a whole bunch of times. So you take the trace of sigma A, where A is x, y, or z, acting on our density matrix rho hat. Then you integrate over P and Q. And that will give you, because we know what P hat is at time 0, the integral over P and Q just completely drops out. And so that will give you h bar over 2 times the trace of, the initial spin configuration times the Pauli density matrix. So we can just add the total spins. So the total angular momentum at t equals 0 is given by this. So the angular momentum in the x direction is the x component of Q naught cross P naught plus the x component of the quantum system, and similarly for y and z. And so the expectation values of the spin operators at time t, now that we know what the initial angular momentum is doing, we can compute the expectation values of the spin operators at some later time, which tells us what the spin is doing at a later time. So again, the expectation value is computed in the same way. Well, we just need to know how it evolves. We need to know what rho hat of t is. But we know what rho hat of t is. Rho hat of t is this thing, right? That's rho hat of t. So we can just plug that in and compute. And you find that actually it's just the only difference is that rather than just having h bar over t times the angular momentum, or times the spin, essentially, the average spin of your quantum system, now it's the angular momentum kind of drops off. It gets smaller as time proceeds forward. The angular momentum, in some sense, is either leaking to the classical trajectory, or it's just leaking out of the system entirely. It's just leaving the system. Now, let's assume that the final state has zero orbital angular momentum. LF is 0, which can be realized by taking, say, your initial position is 0 and your initial momentum is 0. So you just have a particle sitting at rest at the origin of your system. That's the final state, right? What determines the value of kappa? That's just a constant, it seems. In this case, the total angular momentum vanishes at t goes to infinity. So the expectation value of the spin operators is 0. The expectation value of the classical trajectory is 0, because it's just sitting there not moving. And so the total angular momentum would be 0 if you wait long enough. And the solution of 4.3 is given by this guy. So we already know what the solution is. 4.3, the solution is this guy. So you plug in what the final state should be. You know what the initial state is. Well, it just is, yeah, the initial state's just this. So the solution of 4.3, that's the solution of our evolution equation, is this thing. Now, importantly, this is rotationally symmetric. That's the weird thing. So the equation of motion, Fear's interaction, thanks for the $10. Who knew breaking the law could be so nerdy? Yeah, right, tell me about it. But thank you for the $10. So the equation of motion, this guy, is rotationally symmetric, right? Like that's like the whole point. Now, the initial state might not be rotationally symmetric, but the equations of motion are rotationally symmetric, which means that somehow, even though the equations of motion say that, like, if you rotate the whole thing, you get the equations of motion stay the same, somehow, and if this was like a classical or a quantum system, you would expect that would imply angular momentum is conserved. Somehow, the rotational symmetry of the equation of motion doesn't lead to angular momentum conservation. The angular momentum starts out as this, which is essentially arbitrary, and it ends as 0. So the system, it's not like the angular momentum from the spin is leaking to the angular momentum of the classical system. Rather, if you have a classical quantum system that allows for some dissipation, that angular momentum is just disappearing. Like it's just not there. It's just like gone. It's not like leaking out somewhere. It's just disappearing. It's very weird. So let's just read the discussion. We'll call it there. Right. So two types of issues may arise in the construction of a CQ hybrid theory that describes classical gravity and quantum matter. First, consistency requirements such as equation 2.16 must be compatible with the coefficients determined from general relativity and the quantum theory on curved backgrounds. Okay, that's fine. They already checked that. Second, the compatibility with conservation laws present an additional challenge. Yeah, while angular momentum is not conserved in our rotationally invariant toy model, and simple semi-classical back reactions lead to non-conservation of energy, it's not yet known if the scheme proposed in reference 6 exhibits the same properties. That's the Oppenheim paper. If such an incompatibility is indeed present, it is possible that the relevant violation timescale significantly exceeds our lifetime, or even that of our universe. Therefore, even if a hybrid model predicts that conservation laws may be violated in gravity-matter interactions, such violations may not be detectable by quasi-local observables. I'll explain why in a minute, but I'm going to read this super chat from Stinky Ethian for $5. Thank you, Ethian. In figure 4.8, why is it averaging over all directions if spin basis is arbitrary? Figure 4.8. You mean equation 4.8? You mean here? It's not averaging over all directions. So it's averaging over all positions, over all classical configurations. Right. Yeah, I need to explain this. So if such an incompatibility is indeed present, they're basically saying, look, there might be energy conservation violations, but it might be the case that the scale, like the scale of the energy conservation is so small that we just could never detect it as like a localized observer. Oh, 4.6. 4.6. It's not averaging. It's not averaging over all. It's not averaging over all directions. It's averaging over all classical trajectories. On the other hand, exact conservation laws are restored in a suitably taken limit of vanishing dissipative terms. Yeah, so that's the point. If there's no dissipation, then you get conservation laws. Gravity and matter never really decouple, even though for the most part this interaction is relatively weak. This makes the very early universe, where the effective gravitational interaction was strong, a particularly interesting avenue to explore. A complementary analysis showed that a tree-level scattering theory in which classical fields mediate interactions between quantum systems can be formulated in an appropriate limit of the CQ model proposed by Oppenheim and collaborators. Okay, that's just referencing some other paper. While the scattering probabilities are Lorentz invariant in this framework and total probability is conserved, they violate energy momentum conservation, which nobody likes. We like that. This provides further evidence that invariance under spacetime symmetries in CQ models do not, in general, or does not in general, entail conservation of the corresponding Noether charges, and highlights a fundamental structural limitation of hybrid approaches based on CP dynamics. This is just saying, look, another group did another thing, and they came to roughly the same conclusion. By the way, these are dissipative forces, which means that you don't get energy out of the system. You don't get more energy out than you put in. You lose energy. Energy is just lost. Finally, we briefly comment on the definition of the term quantum gravity. The CQ theory describes classical space-time dynamics while at the same time introducing quantum noise that is independent of quantum matter via quantum channels. The introduction of quantum noise is unavoidable in the CQ framework in order to resolve paradoxes that arise in semi-classical formulations of the Einstein field equations. One may therefore argue that in this context, the quantum noise has an inherently gravitational origin. Given that the CQ gravity theory involves with classical spacetime and quantum noise that stems from gravity, it's not unreasonable to refer to it as a type of quantum gravity theory. My nose is so itchy. Although it remains uncertain whether this framework qualifies as quantum gravity in the traditional sense, such as in Euclidean path integral approaches or string theory, it would be equally unfounded at this stage to insist that it must be regarded solely as a classical spacetime theory. Right, so this is just saying, look, does this really count as quantum gravity? Who knows, maybe, sort of, kind of, but it's definitely not a classical theory. So, I'm going to drink some water and then we can talk. Right. So, this was a lot of detail. I mean, like, I didn't know anything about classical quantum hybrid systems before reading this paper. And now I do, which is good. I'm glad that I learned about that. And I don't know, it might even be relevant. Well, it's not relevant for... I'm writing a paper that involves some quantum field theory on curved spacetimes, which is really complicated. It's this one. But this is good to know about because I'm interested in, you know, alternative ways of describing how gravity interacts with quantum mechanics. That's something I'm interested in generally. So it's good to have read this paper because now I have, you know, some more background. But what's interesting, like, it is an interesting consequence that if we're going to demand that, like, you have some classical quantum relation, like hybrid systems, if our universe is genuinely classical quantum, then that means that the conservation laws that we normally think of just might not be genuine conservation laws, which is very weird. So maybe that means that you shouldn't trust these, but on the other hand, it's possible that they hold very nearly, but they don't hold exactly because our instruments are only so good, right? Anyway, so that's the live for today. It's been 2 hours, which is a really long live for this kind of thing because I'm losing my voice. If you guys want to read it, remember, just punch this into Google. Punch this thing on the left into Google, and you'll see it there. I have to sneeze, and I don't want to end the live. I didn't want to be sneezing while ending the live. Right. So thanks, guys, for being here. Thanks for any of the donations that you've given me. I appreciate those a lot. It encourages me to do these more, spend more time doing it. This is definitely the hardest live stream that I do because I actually have to use my brain for it, unlike the other ones. It's not quite true, but it's hard both on the voice and it's hard on the brain. So if you want to encourage me to do this more, you know how to do it. Share the live, donate to the live, subscribe, like, all of these lovely things. Comment if you're watching on YouTube later at some later date. But until then, I will see you guys tomorrow for Ask a Physicist. Take care, everybody.